Okay, so we're going to be looking at a couple of concepts within mechanics, specifically kinetic energy and potential energy, which relates a bit to the work done that we were talking about before. Just before we get started, I thought it'd be worth asking this question, a fairly basic question, but you may have an answer from physics, but it's good to just remind ourselves what actually is energy. Can you come up with a sort of short and sweet definition that describes energy? See what you can come up with, just a sentence, and then we'll see how close it matches what I'm about to give you. Okay, so here is what I would go for. Energy is effectively just a quantity. That's not so helpful so far, but it quantifies something. It's a numerical quantity, but what does it quantify? The potential to do work. That's the way I would phrase it. And when I say I would phrase it, that's the way that most online sources also agree with defining it. It's a bit like asking what is time, because we all sort of intrinsically understand the idea. Time, it's a numerical value. It describes something that you can experience. You've had experience of what it is for time to pass and for it to be a certain time, but what actually is it is a bit hard to describe. It's a bit similar with energy, I suppose. Ultimately, it is just a concept that we have defined in order to explain a certain property of the universe, which is all about the transfer of energy. And ultimately, that is what we're quantifying when we talk about energy. So if you talk about an object having a lot of energy, it means that object has a lot of potential to do work. So, like heat being something that's very hot has a lot of energy, and ultimately, when we say has a lot of energy, we mean it can do a lot of work, right? And work we mean in the same sense as before. And that's it really. So that's what we want to keep in mind. And that is what we're going to be thinking about when we talk about things having kinetic energy and potential energy. It's that they have the potential to do work. Okay, so some of us know already. I'll just quickly throw this out here. The definition of kinetic energy is half mv squared. And let's just clarify what is meant by this. So first of all, the fact that there's an m in this, in other words mass, means that when we talk about kinetic energy, we're talking about the kinetic energy of an object, right, or of an object with mass. So for instance, when we talked about work done, we're talking about the work done by a force, but kinetic energy is the property of an object. And it's the property of an object, and it relates to its velocity. So the faster something is going, the more kinetic energy it has. The slower something is going, the less kinetic energy it has. If something is at rest, then velocity is 0 and its kinetic energy is 0. And because it increases with the square of velocity, it's worth keeping in mind that just because something goes twice as fast, it actually means it has 4 times as much kinetic energy. And it makes sense that something going at a speed has kinetic energy, because again, if we relate it to this idea that energy is the potential to do work, if something very fast hits me, then it can move me. And the faster it's going, the more it can move me. So that's what that kinetic energy is. It's this potential to influence the motion of other objects, effectively. If something's not moving, it has no potential to influence other objects around it. And then just one other point on this. This formula can also work in multiple dimensions. Because remember, that mass is actually a scalar quantity, whereas velocity is a vector quantity. So really, it doesn't make sense to square vectors. So the proper way really to write this formula would be the mod of v squared. And not only does that solve the problem in terms of fixing what otherwise wouldn't make sense, squaring a vector, it also means that it now works in multiple dimensions. So if you have a velocity of an object as a vector form, let's say 2i plus 3j, something like this, then you'd have to find the magnitude of that vector, square root of 2 squared plus 3 squared, and then that magnitude is what you would then use within this formula. Okay, cool. All right, that's it. That's the definition. How that definition comes about, and come up with that a little bit later, I think. For now, we're just going to use it. Okay, so super easy. Just to check, we've done this at least once. You've got a mass, you've got a speed. What's the kinetic energy of the object? And notice that it is referring to the object itself. 1/2 times mass times velocity, magnitude of velocity in this case is 9, square it, and so on, and then you get your number. What would that be? Let me just check. 12.2. 12.15, I think. Yeah, no point rounding it up. 12.15. Joules. Remember, we measure kinetic energy in joules. Or any energy is measured in joules, and that's it. Okay, simple as that. Let's look at our next topic of interest. Okay, so an important concept here to relate work done and kinetic energy. We saw work done as being defined, so by definition it's force times displacement. Again, in the simplified sense, you have to take direction into account. It's force times displacement, but it can also be shown from that definition that this is equivalent to the change in kinetic energy of an object. That is, the kinetic energy before the force was applied, or at least from when you start considering a certain timestamp up to a later timestamp, effectively. So work done is equivalent to change in kinetic energy, and we can also use this to work out one or the other if we have information from either side. To express this as a formula, which would be very useful, I would write it this way. I would say work done equals, and we have this usual notation V and U to describe an earlier speed and or an earlier velocity and a later velocity, and mass, of course, at least at this level, does not change. So we can just write it like this: work done is half mv squared minus half u squared. That's final velocity, and u is the initial velocity of the same object. Again, technically, although it's often forgotten about, we're talking magnitudes here. And that's it. In terms of why that's the case, I think I'll save that for the next part, but for now we're just going to make use of it. Okay, so we've got an example of then using this. You've got a box, its mass is 1.5, across a smooth horizontal surface by a horizontal force. The initial speed of the box is u, and the final speed is 3. So u we don't know, but the magnitude of the final velocity is 3. And the work done by the force, let's use capital W, equals 1.8. Calculate the value of u, this thing we don't know. So it's as simple as just writing out your equation, basically. So we've got that, 1.8. In fact, let's shortcut this and just double everything. So I'm going to change 1.8 to 3.6, so I can get rid of the halves. The mass is 1.5, so let's immediately divide by the mass on both sides as well. So then we just get this, makes it a bit faster, which in this case is equal to 9 minus mod of u squared. Therefore mod of u squared is equal to 9 minus 3.6 over 1.5. And that, I've just checked, turns out to be 6.6. So we get that the mod of u equals the square root of 6.6. And that's it. And calculate the value of u. U, in this case, they actually meant it to mean speed. However, I've been using it as a vector. So I'm just going to, for lack of ambiguity, I'll just say the speed u equals square root of 6.6. And best to, in these cases, actually work out what this might be. It's about 2.57, let's say, to 3 significant figures. Okay, so not too complicated, just making use of the formula, if you trust that the formula makes sense at this stage. Okay, so now let's look at this example. We've got a van, its mass is 2000. It starts at rest, u is 0, at some traffic lights. Then after travelling 400 meters, let's call that S, S is 400. The van speed is 12, V is 12. A constant resistance of 500 newtons acts on the van. So for that, I'm just going to quickly draw myself a diagram so we remember this. And then let's call that there, my distance 400. Here it's going at 0 meters a second, and over here it will be going at 12 meters per second. Okay, calculate the driving force, which can be assumed to be constant. So apparently there's also a driving force. Okay. Oh, there we go. Okay, so since we're going to use energy considerations, let's first let's work out the work that has been done. The work that has been done in order to go from this initial kinetic energy to this final kinetic energy. Since the initial kinetic energy was 0, the change in kinetic energy is just going to be the kinetic energy that it ended with when it was 12 meters per second. So this van has a work done on it of 2000, which is mass, times a half, times 12 squared. So that's just going to be 144,000. Okay, and then technically minus 0, but that leaves the answer as it is. Okay, and then because we've got these two definitions for work done, or one definition and then one sort of second theorem, I suppose, we can equate the two, right? So in this case, we first did difference in kinetic energy, or change in kinetic energy. Now let's also do the force times displacement definition. And for this we need to be a bit careful, because the work done by D in order to produce this change in kinetic energy is not 400 times D. It's 400 times D minus the 500. And intuitively this does hopefully make sense. The reason being is this, that D is doing a lot of work, right? It's pushing this van, or pulling, it depends how you can think of driving force, but that driving force is taking the van to the right, and in doing so it's doing work, and some of that work is being used to overcome this resistive force, presumably some sort of friction of 500 newtons. So it's using some of its work, it's doing some work on resisting that force, and then whatever remains is what's being used to increase the kinetic energy of the object. So if you imagine, for instance, that D, that driving force, was 500, then you'd have a net force of 0, so it'd be going at constant speed. So a driving force of 500 would result in exactly no change in kinetic energy. So that, therefore, it makes sense that you would just deduct the 500 from D in order to work out how much of that force is actually being used to increase the kinetic energy of the object. So that's the work done by the force, is D minus 500, this driving force. Let me just write that D a bit better. Times the distance, right? And that should be, those two should be equal. That's equal to 144,000. Okay, and then from this we should be able to get our answer, which if we work it out, we get D minus 500 is 360, so therefore the driving force is 860 newtons, and that's it. Okay, now let's define potential energy, which is a bit different to kinetic energy. Quite often we drop a certain word, and I have done here as well. When we talk about potential energy, by default we're talking about gravitational potential energy. I mean, technically all energy isn't, a lot of energies in some sense are potential, in that that's what we said the definition of energy was. We said energy is the potential for something to do work, right? So if I have I don't know, a battery, and if I haven't connected anything to it yet, then there is some sort of potential energy in there, right? There's some energy that can be used and effectively be used to do work. But by default, when we say potential energy, we mean gravitational potential energy. This is the energy that any object within a gravitational field has got because of the fact that it's off the surface of a mass. It's a bit of a funny idea, because I suppose everything in the universe has some gravitational potential energy, and it's not just to do with the Earth. You have potential energy gravitationally with respect to every other object in the universe. It's just that the Earth is the most concerning mass at the moment. It's the biggest and closest one to us. So we tend to talk about gravitational potential energy with respect to the Earth and disregard all other objects because they're either too small or too far away. So do just keep that in mind. And we also simplify a little bit. At a more advanced level, you'd realize that gravitational force is not actually constant. It's not actually 9.81, for instance. In most of the universe, it just happens to be that value when you're walking on the surface of the Earth, or you're fairly close to it. So we simplify a bit within this change of potential energy that we're about to look at, but for most of our purposes it will do. So here's how we define it. Potential energy equals mgh. So it probably looks familiar, right? This looks just like the work done against gravity, which makes sense, right? Because in the same way as we said work done is the change in kinetic energy, the work done against gravity is also the change in potential energy. The reason why we don't have two terms, one minus the other, is because by default we tend to say that wherever an object started at, it had 0, and then whatever it changed to, which we call the h is the change in height, which could be positive or negative, that is its new potential energy. A big part of potential energy, defining potential energy, is choosing a 0 level. So most of the time we'll just say wherever an object currently is, that's its 0 level, and then if you change its height, so you lift it up or you somehow lower it, that's your h value, and then you multiply by mg and you've got the new potential energy. So potential energy can actually be negative as well, but really it's all about defining it relative to other objects, right? So there isn't really an absolute value. It doesn't, because it depends how you pick your zero level. So if the zero level is the Earth, let's say, that's your zero level, and I've got an object here. That object has got no potential energy, and then if it's up here, and let's say that's 2 meters, then its potential energy is now 2 mg, right? And down here, if I go down a meter, well, let's say 3 meters, m is meters, now it's minus 3 mg. And then, of course, we've got other objects going on. The key point is that they all share the same zero level. Okay, 0 is an arbitrary level, and it's with respect to that 0 that you define the potential energy of all objects in the universe. And for any particular problem that you're currently working on, you'll have a defined 0 level, and as long as it's consistent throughout your calculations, then you will get an answer that makes sense. Everything will be consistent. Okay, so we'll look at one very basic example, and then I'll let you do some questions. Okay, so let's look at this example. A load of bricks, technical term, of total mass 30 kilograms is lowered vertically to the ground through a distance 15 meters. Find the loss in potential energy. So the mass is 30. The H, I guess, is technically minus 15. It doesn't really matter if we say minus or plus in this sense, because we know our final answer, we're just going to choose the positive version. So then we literally just do mgh, and we say, okay, that's g times 30 times minus 15 equals minus 450 g, and what does that come to? Minus 4,410, and the loss, it's gone down by minus 4,410 if we say it initially was 0. But as a final answer, we'll just say 4,410, because to say how much has been lost, that's ultimately a positive quantity. So slightly funny phrasing, but that's it. 4,410 joules. That's it. You just do mgh. That calculation we did here, that was assuming the 0 level was where it started. If you did it the other way around and said the 0 level is where it ended, then all that means is it started with 4,410. It ended with 0, you still get a difference of minus 4,410. The point is the change in potential energy will always be the same, regardless of where you put your 0 level. Even if you put it in the middle, if you put it at 8 meters or something. So to say an object has a specific potential energy, that's kind of loose and ambiguous. It depends on what 0 level you're working with. But the change in potential energy, that will always be consistent, regardless of if two different people looking at the same thing have different 0 levels. So that's it, 4,410 joules, nice and simple. Okay, so then done a bit of explanation. These questions then are going to be nice and easy to do, I think. It's just this slide and the next. Really to just make sure that you're comfortable with all of these concepts. Part 2, second video to this, we can go through some more sort of actual problem solving kind of questions, but for now let's just do some basic calculation and see if we agree. Number 1, I mean it's simple arithmetic really, but I guess I kind of like it because, I mean, think about, don't just like obscure everything but the numbers. Actually read what it's saying, and then you can also start to get some intuition for these things, like ultimately which one is having more energy, right? Is it an arrow at a given speed, or is it a car at a given speed? And these are all sort of typical masses and typical speeds. So at least I think it'd be quite interesting to do this, rank them, and then you'll get some intuition about what has more kinetic energy and what doesn't, because it might not be obvious to you at this stage, having not multiplied many masses by their velocities squared before. Okay, so just quickly run through these, and then there's one more quick one on the second slide. You can pause. Okay, and then just quickly do these ones.